Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we're going to work on Self-Test 2, Form B. And basically, I will give you the same admonition before each of these exercise sets. Make sure that before you watch me do Form B for you, no matter what module we're doing, that you have at least tried all the problems in Form A first. That way you'll get the maximum value from my comments and the commentary. And without any further admonition, let's go over to the board and let's see how these 10 problems go, okay? So today this is going to be the solution set for Self-Test 2, Form B. And the first problem simply says add, and they write in vertical form, 461,704, 206,813, 21,483. And notice again, since we always assume in addition that the numbers are adjectives modifying nouns, we have to line these up from the left. In other words, when you say that 3 and 3 is 6, you have to say what? 3 ones and 3 ones are 6 ones. So you can't say 3 plus 1 is 4, because the 3 here is modifying 1s, but the 1 here is modifying 10s. So once you understand that, we just sort of whiz through this, you see. 3 and 3 is 6, plus 4 is 10. Put down the 0, carry the 1. You see we're trading in all 10 ones for 1 more 10. 8 and 1 are 9, and 1 are 10. 10 what? 10 tens, which we trade all of those in for 1 more 100. See what's happening here? When I say 4 and 8 are 12, I'm saying 400 and 800 are 1200. See, and 7 more is 1900. But the hundreds are being taken care of by the placeholder just by being in this column. You see, I know it's 1900, and 1 more is 20, so I put down the 0 and carry the 2. Then 1 and 6 are 7, and 1 are 8, and 2 are 10. 10 what? 10 thousands, which I trade in for 1 10,000. 2 plus 6 is 8, and 1 are 9. 9 what? 9 10,000s, just by putting this down here, and 2 plus 4 is 6. And notice, by the way, the 6 was the most important digit, and the way we usually do this, I find the most important digit last. In other words, when I'm the tiredest, and I'm in danger of, best danger of making a mistake, I'm going to make it in the column that counts the most. That's why later on we're going to find ways to estimate these sums. But what I'd like you to get used to is when you see a problem like this, look at this number over here. It's more than 400,000. This is more than 200,000. So the answer is more than 600,000. And this is less than 100,000. So we're in the 600 to 700,000 range. I want you to get a feeling, what I call a number sense for this. Problem number 2 is exactly the same type of problem as number 1, only for 2 slight differences. The first is, to get you used to the vocabulary, I use the word sum, S-U-M, which indicates what? The answer to an addition problem, rather than to tell you to add. And the second thing is, I use the horizontal form rather than the vertical form. And the danger with the horizontal form is that you may misread the nouns that the adjectives modify. You see, if you're using a calculator later on, there's no danger writing the thing in horizontal form. Let me show you what the danger is if you try to do the problem in horizontal form and you're not careful. You say, gee, the first digit here is a 4, the first digit here is a 1, the first digit here is a 5, so I'll add the 4, the 1, and the 5 to get 10. Well, you see, 4 plus 1 plus 5 is 10, but that's only if 4, 1, and 5 are modifying the same noun. Notice that the 4 over here is in the 10,000s place. The 1 over here is in the 100,000s place. You see that? And the 5 over here is in the thousands place. You see, the 4, 1, and 5 are adjectives modifying different nouns, so we can't add them that way. So if you're not using a calculator and you don't feel like doing mental gymnastics and keeping track of the denominations, it's reasonable to rewrite the problem in the vertical form so that the like denominations line up. In other words, we write 43,234. Then we write the 123,806 so that the ones are lining up. You see, once the ones are in place, every other denomination is also in place. Then we get what? The 5,082. And we say what? 4 plus 6 are 10 and 2 are 12. Put down the 2 and carry the 1. At this point, you may say to me, wait a second. Last time we did the problem in vertical form, you started at the bottom and worked to the top. Well, remember, addition is commutative. The order in which you add the terms does not make a difference. It's also associative. That means if you regroup the terms, it doesn't make a difference. And if you just feel like fooling around this way, if you don't make a mistake, no matter how you permute the order here, the answer is going to be 12. See, if I say 6 plus 2 is 8 plus 4 more, the answer is still 12, isn't it? So don't worry about how you go. Just make sure you don't make mistakes in the tables. And notice that no matter how complicated these problems are, you're never adding more than a single digit at a time onto the next sum. You see what I'm doing here? See, 8 and 3 are 11. 11 plus 1, 11, 12. See, put down the 2, carry the 1. 8 and 2 are 10, and 1 more is 11. Put down the 1 and carry the 1. 5 and 3 are 8, and 3 more are 11. See, a single digit at a time. 11 plus 1 is 12. Put down the 2 and carry the 1. 2 plus 4 is 6, and 1 is 7. Put down the 7, and then the 1 over here. The answer is 172,122. You start to see a number sense to this. You get a feeling for it. You see, it is important that you get the right answers. It's more important that you understand why it's the right answer and what it means. Okay? Now, I mentioned before that when you deal with multi-digits, you tend to do the most important digits last, and sometimes we like to get estimates. So let's review rounding off. See, problem number 3, part A says, round off 92,983,840 to the nearest thousand. Now, what does to the nearest thousand mean? It means that we want to look at this column over here, the thousands column. Well, take a look at this. You see, if you ignore the 840, you're between 92,983 and 92,984. Which multiple of 1,000 are you closer to? Well, since this digit over here is an 8, that means you're closer to the next higher multiple than to this one here. In other words, since this is more than halfway between, you change the 3 to a 4, drop everything else, and so round it off to the nearest thousand. This number would be what? 92,984,000. So you still read the 92 million part, but now what we're saying is what? If you were counting by thousands, this would be what? Between the 92,983rd thousand, 92,984,000, but closer to this one. Okay? So I round this off to the nearest thousand. Part B gives me the same number, but it says round off to the nearest million. Now you see, where's the million place? The million place is over here. See, units, thousands, millions. This is 1 million. This is 10 millions. So I want to round this off to the nearest million. You see, what this says is, if I'm counting by millions, I eventually get to 92 million, don't I? This number here is more than 92 million. But when I'm counting by millions, the next number I come to is 93 million. 93 million is bigger than this number, so this number must be where? Between the 92nd multiple of a million and the 93rd multiple of a million. But now, which one is it closest to? Well, the fact that this is a 9, that's more than halfway. It means that I'm closer to the next multiple than to the 92. So what do? I change the 2 to a 3, and then replace all the other digits by zeros. And so rounded off to the nearest million, the answer is 93 million. Notice that the answer to B and to A are different because I'm rounding off to a different noun. You see, what happened in part B is I was ignoring more digits, so the answer came out simpler. In other words, the more digits I ignore, the less non-zero digits I have. See, this was all the way out to the nearest million, so I could ignore these first 6 places. This one up here, on the other hand, was to the nearest thousand, so I had 5 digits to worry about. And now to complete problem number 3, suppose I say round off the same number, 92,983,840, to the nearest 10 million. You see, this is the 10 millions place. See, this is the millions, 1 millions, 10 millions. How many 10 millions do I have? You see, I have 9 10 millions. This is a little bit tricky, and I just thought I'd like to show you a different way of seeing this. You see, when I'm counting by 10 millions, the 9th 10 million is what we call 90 million. See, 9 10 millions is 90 million. Why is that? 9 tens are 90. 10 10 millions are 100 million. You see, in place value notation, 9 10 millions would be called 90 million, and 10 10 millions would be called 100 million. But when you're counting by 10 millions, there's nothing between 90 million and 100 million. And what number is halfway between 90 and 100? It's 95. So this number here is the halfway point. Now, what number are we dealing with? We're dealing with 92,983,840. And where is that number? That's between 90 million and 95 million. In other words, the way we do this, I'm going to review the short way, but I just wanted you to see on one of these problems what you're really doing here. See, what you're really showing is that when you count by 10 millions, 92,983,840 is between 90 million and 100 million. But because it's less than 95 million, that makes it closer to 90 million than to 100 million. So rounded off to the nearest 10 million, the answer is what? 90 million. Now I want to go back to the top of the board in a minute just to show you the short way of doing this, but I just want you to see what the answer is here. You see 92 is between 90 and 100, but closer to 90. 90 what? 90 million. Now you see the short way of doing this problem is you come back here, you want to round this off to the nearest 10 million, you look at the digit immediately to the right, that's less than 5, so what do? You drop all of these places and just leave the 9. You see that? Because this was less than 5, I put the 9 over here, and the other 7 digits get replaced by zeros. That's the short way, but this is the logic behind it. And now that we know how to round off, let me show you how we find estimates to an addition problem by rounding off. Let's do the next problem, problem number 4. Problem number 4 says, by rounding off each term. Remember, a term is what we call each number that's being added. By rounding off each term to the nearest 1,000, estimate the sum 56,897 plus 18,023 plus 21,989. Again, we use the vertical form if we were going to get this answer exactly correct. But now what we say is, look, if you were counting by thousands here, see, where is 56,897? If you're counting by thousands, it comes after 56,000, but before 57,000. Since this is an 8, that means you're more than halfway, so the 56,000 becomes 57,000. In other words, you're between 56,000 and 57,000, so you round that off to 57,000. And notice that I'm using the noun thousand rather than 3 zeros to emphasize that when I'm estimating this way, I'm only going to be adding 2-digit numbers, not 5-digit numbers. You see, if I'm counting by thousands, 18,023 comes between 18,000 and 19,000, but the 0 over here tells me I'm closer to 18,000, so rounded off to the nearest 1,000, 18,023 becomes 18,000. 21,989, see, that's between what? When you're counting by thousands, it's between 21 thousands and 22 thousands, but the 9 over here tells me that I'm closer to 22,000, so rounded off to the nearest 1,000, 21,989 is 22,000. Now you see what happens here. 57, 18, and 22 are adjectives modifying thousands. So I can now add this up and get what? 50, see, 2 and 8 are 10 and 7 are 17. Put down the 7, carry the 1. 2 and 1 are 3 and 5 are 8 and 1 is 9. The answer is 97,000. And if you feel more comfortable with digits rather than with words, you simply write this as what? 97,000. And this tells me that the answer is around 97,000. Just for the heck of it, let's find the exact answer. See, 9 and 3 are 12, and 7 are 19. Put down the 9, carry the 1. 8 and 2 are 10, and 9 are 19, and 1 is 20. Put down the 0, carry the 2. 2 and 8 are 10, and 9 are 19. Put down the 9 and carry the 1. 1 and 6 are 7, and 8 are 15, and 1 is 16. Put down the 6 and carry the 1. 1 and 5 are 6. 1 is 7, and 2 are 9. The exact answer is 96,909, and my estimate was what? 97,000. Huh? Aren't you glad to know me? Neat, isn't it? By the way, we can even do better than this. See, notice that if we wanted to be even surer of what we're doing, if we didn't feel like rounding off, what are we sure of? That 56,897 is between 56,000 and 57,000. You see, 56 would be a lower bound, 57 would be an upper bound. In the same way, 18,023 has to be more than 18,000 but less than 19,000. And 21,989 is more than 21,000 but less than 22,000. Now you see I add these numbers up, I add these numbers up, and now not only do I know that the answer is around 97,000, but I also know what? It has to be more than 95,000 but less than 98,000. In other words, no matter what kind of a mistake I made, if I wound up with an answer that was less than 95,000 or more than 98,000, no matter what the right answer is, I would know that my answer was wrong. Now, the biggest flack that I get in trying to teach people to round off is they say to me, look, I can understand where people would round off in the pre-calculator days. But now that we have calculators, why even round off? Just punch the digits in, no matter how many there are, and get the exact answer. Well, the problem is that sometimes you are dealing with a number of digits that either the calculator can't handle, or which there are so many of that even if the calculator can handle it, you tend to make careless mistakes. Just like on a typewriter, you want to type an E and you hit an R by mistake. Or you want to type an A and you hit a Q. I used the wrong hand. Whatever it happens to be. Do you see what I'm saying? You can always make what we call transpositional errors. So to help you get used to this, the next problem gives us lots and lots of digits, but it's technically the same problem that we just dealt with. It says by rounding off each term to the nearest trillion, estimate the sum 5,299,760,998,778. Heck, that's taking me a long time just to pronounce. What a messy problem this is. But you see, a lot of times you don't care about what we call the small change, the nickels and dimes. When you're on a billion-dollar contract, if you ignore a few pennies, or even a few $100, or even a few $1,000, there's no real harm done. What you don't want to do is to ignore $1 billion. So basically what we do is, you would count by saying, what, this is the units, thousands, millions, billions, here's the trillions place. So how many trillions do we have here? Counting by trillions, this would be more than 5 trillion, but less than 6 trillion. So rounded off, this would become what? 5 trillion. Looking over here, this is between 3 and 4, but the fact that this is a 9 means that we're closer to the 4. So if we round it off over here, this would round off to 4 trillion. See, all the trillions, see the place value? Once I've located the trillions in one of these numbers, I have them in all of these numbers. You see, counting by trillions, this number here would come up after 4 trillion, but before 5 trillion. So this is between 4 trillion and 5 trillion, but the 8 over here tells me that I'm closer to 5 trillion. Counting by trillions, this number is more than 2 trillion, but less than 3 trillion. The 0 here tells me this is closer to 2 trillion. And by the way, I should warn you of this. Students a lot of times see all these 9s and 8s and say, boy, isn't that a lot? All that matters is this digit over here. You see, once this is a 0, this digit here can't do much over here. If you don't see what I'm saying here, think of it in terms of money. See, $2.10 is more than $2.09. You see, the 9 over here doesn't offset the 1 over here. So you've got to be very, very careful about that. But by the way, to show you what we really did over here, and why this is really the same as the previous problem, without even looking at this number over here, I could say right away that it was what? Between 5 trillion and 6 trillion. This number was between 3 trillion and 4 trillion. This number was between 4 trillion and 5 trillion. This number was between 2 trillion and 3 trillion. And so what I did was I tabulated what I call the lower bounds. See the answer that's too small, the lower bound, and the upper bound. See, in other words, the first number was between 5 and 6 trillion, but closer to 5. The second number was between 3 and 4 trillion, but closer to 4. The third number was between 4 and 5 trillion, but closer to 5. The fourth number was between 2 and 3 trillion, but closer to 2. Now you see, look what happens. with the noun being taken care of by the word trillion, to get the estimate here, I just have to add these 4 single digits. 5 and 4 are 8, and 4 are 12, and 2 are 14. 14 trillion is too small to be the right answer. 6 plus 4 is 10, plus 5 is 15, plus 3 is 18. 18 trillion is too big to be the right answer. And rounded off, I get what? 5 trillion and 4 trillion is 9 trillion, and 5 more is 14, and 2 more is 16. And so now I know what? That the correct answer to this problem, no matter what else, has to be between 14 trillion and 18 trillion, but closer to 16 trillion. And I don't have the time, and if I did have the time, I don't find it exciting to find the exact answer to this problem. But if you'd like to see how it works, why not take a few seconds, well, maybe more than a few seconds, add the whole thing up and see if the answer comes out in the right range. And if it does, you'll see the beauty of making a fast estimate. And if it doesn't, you'll even see the beauty more, because the fast estimate will warn you that you've made a mistake. All right? Well, so much for reviewing addition. Let's now get on to reviewing subtraction. And by the way, just one more remark before I do that. Notice again the psychological difference between writing 16 trillion, in which the only adjective you see is 16. You see, the word trillion takes care of the rest. Versus writing what? No units, no thousands, no millions, no billions, but 16 trillion. You know, if somebody wants to show you that they're spending a little bit of money, they're never going to write the budget as $16 trillion this way. Those zeros look scary. But if they write this, all you see is the 16, and all those zeros are covered up by the word trillion. And you don't even notice that sometimes. Notice, in other words, the psychological impact of the place value notation versus the adjective noun notation. Okay, at any rate, the next problem says write 84,015 minus 9,867 as a place value numeral. Now, the first thing that happens over here is that most people say, what the heck is he talking about? What does he mean, write this as a place value numeral? Well, the point is that this is a place value numeral and this is a place value numeral. You see, this is one number and this is another number. These are what? Altogether 2 numbers. But the difference of 2 numbers is only 1 number. You see, what I'm really saying is, what's the answer to this problem written as a place value numeral? And I guess to show you this with an easier thing, see, 6 is 1 number and 4 is 1 number. 6 and 4 are 2 different numbers, is that correct? But when I put a minus sign in front, 6 minus 4 is only 1 number. What number is it? The number which, when you add it to 4, gives you 6. So I just want you to get used to that. See, 6 is 1 number, 4 is another number, but 6 minus 4 names the same as the single number 2. And so all this is really asking you to do is to take 84, in the vertical form, is to take 84,015 and subtract 9,867. And you remember how we do this? We can't take 7 from 5, so we go to the tens place. We take the 1 10 that we have, trade that in for 10 ones. So now we have no 10s and 15 ones. 7 ones from 15 ones is 8 ones. See, we write that 1 very small, so it looks like it's still in the ones place. You don't want to create, remember we said only 1 digit per place value column? See, the 1 is written small and very close to the 5 to create the illusion that it's still in the ones place. Now you can't take 6 from 0, so again you want to trade in. You have no hundreds to trade in, so you go to the thousands place. You trade in one of your thousands, leaving you with 3. What do you trade them in for? 10 hundreds. Well, that means just put a 1 in front here. Now you take one of your 10 hundreds, leaving you with 9. Trade that 1 in for 10 tens. Now you can say what? 6 from 10 is 4, because 4 plus 6 is 10. 8 from 9, in other words, 9 take away 8 is 1. Now you can't take 9 away from 3, but what you can do is go to the next place, trade in one of these, which happens to be 10 thousands, but that's not important. You see, whatever you take in one column is worth 10 in the column immediately to the right. This leaves you with what? 7 10 thousands, but 10 more thousands. And to add 10 onto 3, you just put a 1 in front of the 3. That's what the word 13 means. Teen means plus 10. 13 means 3 plus 10. 14, 4 plus 10. Just put the 1 in front. See, 9 from 13 is 4. and then you bring down the 7. You're not taking anything away from it. So the answer to this problem is 74,148. Okay? Hope you understand that okay. And by the way, I'm doing this purely mechanically on purpose to lead up to a smashing climax. You see, problem number 6, 7, and 8 are going to be a trio. And 8 is the Act 3 that I want you to really see what we're talking about here. Problem number 7 says subtract 9,867 from 84,015. This is something I will do several times in the course. I will give you the same problem with different vocabulary, just to make sure that you understand it's the same problem. See, how do you subtract 9,867 from 84,015? Well, I mean, if that's too complicated, how would you subtract 4 from 6? You'd put the 6 on top, then subtract the 4. So what you would do is what? Write the 84,015 on top. Then you would subtract what? 9,867. See, you're subtracting from. Now, once I do this, do you notice something interesting? I don't have to do any more. This is exactly what? Problem number 6. Problem number 6 said, do this problem. It's the same problem. So 6 and 7 have the same answer. Now let's look at problem number 8. Problem number 8 says, what must you add to 9,867 to get 84,015 as the sum? Again, be careful here. If you read this too fast, what does this problem sound like? It sounds like an addition problem. See, look at the buzzwords. What must you add to get something as the sum? But if you read this thing carefully, it doesn't say what happens if you add 9,867 to 84,015. It says, what must you add to 9,867 to get 84,015 as the sum? You see, because the blank is on the same side as the plus sign, this may look like an addition problem, but it's really what? A subtraction problem. And again, if these things confuse you, just put in smaller numbers. If you had 4 plus blank equals 6, the answer to that problem is what? Not 10, it's 2. And how'd you get the answer? You subtracted the 4 from the 6. So, the interesting point is, to do problem number 8, you've already done that when you did problem 6 and 7. In other words, the amazing thing is, if I were to now add up these two numbers, that would give me this one. Let's just check it out. Do you see what I'm saying here? See, 8 plus 7 is 15, carry the 1. 4 and 6 are 10, and the 1 you carried are 11. Okay, carry the 1. 1 and 8 are 9, and the 1 that you carried is 10. Put down the 0, carry the 1. 4 and 1 are 5, and 9 are 14. Put down the 4 and carry the 1. 7 and 1 are 8. In other words, 74,148 is the number you must add to 9,867 to get 84,015 as the sum. You see that? You see the difference? You see that? And by the way, suppose you hadn't done problem 6 and 7 first. Could you have done this problem as a pure addition problem? And the answer is yes. Namely, what you could have said is, look, this is what we call the change-making method. I'll start with 9,867 and see what I have to add on to this to wind up with 84,015. Well, see, to get from 67 to 75, you have to add on 8. Okay? To get from 875 to 915, you have to add on 40. To get from 9,915 to 10,015, you have to add on 100. And to get from 10,015 to 14,015, you have to add on 4,000. Okay? And to get from 14,015 to 84,015, you have to add on what? 80,000. So altogether, you've added on what? 84,000. I'm sorry, you have to add on 70,000. To get from 14 to 84, you add on 70. And so altogether, I've added on what? 74,148, which is exactly the same answer I got this way. And again, let me remind you that when I figured out what to add on to 9,867 to get 84,015, I happened to pick the way that gave me one digit at a time. See, I first got the 5, then the 1, then the 0, then the 4, then the 8. Any way I do this problem in which I don't make a numerical error is correct. In other words, in terms of making change, I could have started by first adding 3 onto 9,867 to get 9,870. Then I could have added on 30 more to get 9,900. And I'm keeping track of what I'm adding on over here, you see. Then I add on another 100 to get 10,000. Then I add on 70,000 to 10,000 to get 80,000. And then from 80,000 to 84,015, I have to add on 4,015. So if I now add up all the numbers I had to add on to 9,867 to get 84,015, I still wind up with what? 74,148. The exciting thing about a math problem is that if it's well defined, there may be only one right answer, but never only one right method. See, I'm just trying to show you typical ways of doing this. Hopefully, by my experience, I will hit on ways that make sense to you. But every so often, you will have a unique way of trying to do a problem, and while the way I do it may be right, it may not relate to the method that you want, in which case you should check with, say, a tutor, a teacher, a fellow student, and just get these things straightened out, okay? But here's the important point. If you could do problems 6 and 7, but not 8, that means you have a conceptual problem. In other words, if you can do 6 and 7, that means you know how to subtract mechanically. But if you don't know that when you say that 6 minus 4 equals 2, that 2 is the number that you have to add on to 4 to get 6, then what that means is you may be able to do subtraction, but you don't fully comprehend it. And the danger with that is if you can't comprehend it, you're going to get wrong answers to real-life problems. But we'll talk about that more a little bit later in this discussion. There's only a couple of more problems to do, and we might just as well go through them. See, I just want to introduce some new language again. Number 9 says find the difference, 90,004 minus 32,276. And whenever you see the word difference, just like sum, S-U-M, tells you it's an addition problem, difference is going to tell you that it's a subtraction problem. So we're going to actually take 32,276 away from 90,004. And here's the way we do that. I'll do it the mechanical way first, then explain to you another way of viewing borrowing, okay? See, I can't take 6 from 4, so I want to trade in. But I have nothing to trade in here. I have nothing to trade in here, nothing to trade in here, but I can take 9 of whatever this denomination is and trade that in for 10 of the next denomination. You see what I'm doing here? Now, given this 10, I can keep 9 of them and trade 10 of them in for 1 more of the next lower denomination. Then, given 10 of these, I can trade in 1, leaving me with 9, but getting 10 of this denomination. See, now with my 10 tens, I can take 1 of those, leaving me with 9 tens, and trade those in for 10 more 1s. And now you see I'm ready to go on this. See, 6 from 14 is 8. 7 from 9 is 2. 2 from 9 is 7. 2 from 9 is 7. 3 from 8 is 5. And by the way, if you don't understand whether you made a mistake here or not, what's the quick check? Add these 2 numbers and make sure that you get this one. Remember, the answer to this problem is what? The number that you must add to 32,276 to get 90,004 as the answer. And you see, what we really did with this was we started out with what? A 9 in the 10,000s place and a 4 in the 1s place. See, I don't need the zeros here because the denominations are visible, but I can put them in if I want to. And you see, what I did was I took 1 of my 10,000s, leaving me with 8 of them, and traded those in for 10,000s. Then I took 1 of the thousands, leaving me with 9 of them, and traded those in for 10 hundreds. Then I took 1 of my hundreds, leaving me with 9 of them. I traded those in for 10 of these. Then I took 1 of these and traded it in for 10 ones. So all I did is in effect, I rewrote 90,004 as 80,000 plus 9,000 plus 900 plus 90 plus 14. Then you see, when I subtract 32,276, I never have to take away more than what I have, you see. 6 from 14 is 8, 7 from 9 is 2, 2 from 9 is 7, 2 from 9 is 7, 3 from 8 is 5. And you'll notice that what I did here is simply elongating what I did over here. Okay. Now, we showed that when you wanted to add several numbers, you only had to add two at a time, because by the commutative and associate properties, you could then combine more than two numbers at a time. We also mentioned that subtraction doesn't work this way. In fact, before I get to problem number 10, let me just write down a footnote over here, I guess. Let's see how I can do this. Let me just write over here for a second, and then we'll go back up to the top. Suppose I write down 9 minus 3 minus 1. See, look at that. There are two ways to group this. I can say first subtract 3 from 9. See, 9 minus 3, take away 1. And remember, in mathematics, everything inside parentheses is one number. See, so 9 minus 3 is 6. 6 minus 1 is 5. But I could also have read it as 9 minus 3 minus 1. You see, if I erase the parentheses in both of these problems, don't they both look like 9 minus 3 minus 1? But now you see, since everything inside parentheses is one number, I perform 3 minus 1 first. That's 2. 9 take away 2 is 7. In other words, the answer to this problem depends on how the numbers are grouped. You've got to use the grouping symbols here. And all I do in problem number 10 is I give you the same principle, but to disguise it and elevate it a little bit more, I put in slightly bigger numbers. You see, problem number 10a says, find the value of 8,256 minus 3,768. Then I pause. You see the voice inflection problem, minus 1,273. You see this says, first of all, subtract the 3,768 from 8,256. And that's what I do over here. And leaving out the details, I subtract 3,768 from 8,256. I'm going to get what? 4,488. And we'll just leave the details to you. I think that part's easy enough at this stage. The important point is what? That just stands for the 4,488 just stands for what's in parentheses. What's the next step? The next step says take what was in the parentheses, namely 4,488, and then do what? Subtract 1,273. And if I subtract 1,273 from 4,488, I get what? 3,215. That's an easy one. See, 3 from 8 is 5, 7 from 8 is 1, 2 from 4 is 2, 1 from 4 is 3. So that's the answer to part A. Now look at part B. Part B and part A look exactly the same if you erase the parentheses. See, without the parentheses, both A and B look like 8,256 minus 3,768 minus 1,273. But see, everything in parentheses is one number. So now we have to use the voice inflection principle. Now what we say is take 8,256 and subtract 3,768 minus 1,273. See, I'm treating this as if it was just one number. You see, now to do what's in the parentheses first, what am I going to do? I'm going to start with 3,768 and subtract 1,273. If I subtract 1,273 from 3,768, you see what happens over here? 3 from 8 is 5. 7 from 16 is 9. 2 from 6 is 4. 1 from 3 is 2. Notice as we go along here, I become a little bit more debonair about borrowing. I assume that once I teach you this, we can go faster the next time. All I said here was what? Trade in one of your hundreds, leaving you with 6 hundreds, then add 10 tens onto the 6 tens to get 16 tens. Anyway, getting back to our immediate problem, all that part shows me is that the part inside the parentheses is 2,495. Now what does the problem say? The problem really says find the value of 8,256 minus 2,495. So now I take the 8,256 and subtract 2,495. See, 5 from 6 is 1. 9 from 5 I can't take, so I borrow. 9 from 15 is 6. 7 from 1 I can't take, so I borrow again. 4 from 11 is 7. 2 from 7 is 5. So now the answer to part B is 5,761. And what was the answer to part A? 3,215. And you see, just by changing the grouping, the whole meaning of the answer changed. And you say, well, Who cares? Why would you want to know how to group? Let me conclude today's lesson by showing you two, well, in quotation marks at least, practical applications. Let me show you two different real-life situations, one of which would be solved by doing the arithmetic problem in Part A, and the other of which would have been solved by doing the arithmetic problem in Part B. Here's Part A. I tell you that you have $8,256. Let's say that's your business budget. Now, from that budget, you spend $3,768. After you've spent that, you now spend another $1,273. 10A says you have $3,215 left. In other words, how would you solve this problem? You had $8,256. You spent $3,768. So I would first subtract the $3,768 from the $8,256 to tell me how much money I have left. Whatever that sum is, you see, I first subtract this from this. This is now one number. And from that, I now subtract the $1,273 to find out how much money I have left. That would be like a bank withdrawal type of thing. You have so many dollars in the bank, you withdraw part of it, then you withdraw another part, so you subtract what? Sequentially. The first number minus the second, then you subtract the third from that answer. Now, let me give you a completely different problem. Watch how different problem B is from problem A. Remember what problem A was now. You had what? $8,256. You spent $3,768. Then you spent another $1,273. Problem B says you have saved up $3,768 towards a goal of $8,256. Maybe you're going to buy a car for $8,256, and you've saved up $3,768. All of a sudden, there's a crisis. And from that $3,768, you have to pay your parking tickets, $1,273. Now, you see what's happening now. Where is that $1,273 coming from? It's coming from what you already saved. You're spending part of what you saved. I have to subtract the $1,273 from the $3,768. That's the money that I have left. Now, that amount gets subtracted from $8,256 to tell me how much money I still have to raise to buy my car. You see, the answer to Part B, namely $5,761, in this case dollars, is the amount I still need to reach the goal of buying the car. Now, here's what I'm driving at. First of all, if you can't subtract, we have a problem. If you can subtract, but you can't distinguish 10A from 10B, we also have a problem. And if you can distinguish 10A from 10B, but you can't do application A and application B because you're afraid of word problems, what's the sense of knowing how to subtract? But you see, for the first 8 modules of this course, our format is going to be to make sure you understand the computational techniques. I will explain you both the skills and the logic behind it. I will throw in just enough practical applications so that you can see that it's working. Then the last third of our course, namely modules 9, 10, 11, and 12, will be devoted exclusively to showing how you take arithmetic and apply it to solving problems in the real world, which when all is said and done is why 98% of all people who take mathematics want to take mathematics. And what you're going to see as we go along is don't get impatient. Don't say, my golly, we're just working with addition and subtraction of whole numbers. We are going to proceed one step at a time. And by the time we finish our 12 modules, you'll be doing some very sophisticated problems in which, if I'm successful, you'll never have noticed that we did more than one small step at a time. At any rate, that's enough, I think, for this exercise set. Next lecture will be on Module 3, which is called Multiplication and Factoring of Whole Numbers. Until that time, take it easy, stay young, study hard. I look forward to seeing you again real soon.